Okay, good evening. Welcome to
FamilyMath1162.
FamilyMath1162. So yesterday I learned a really cool fact about the Cantor set online, and it was in a Twitter thread by Jordan Ellenberg, and I just forgot to look up the name of the person who posted this link, but I'll write it in the blog, so I apologize for missing one of the names. But it was a really neat fact about the Cantor set that I had not known before. And so first I need to explain to you what the Cantor set is. And so if we start, I don't know if it's supposed to be open or closed, so I'm including 0 and 1 or not, but I guess it doesn't really matter that much. So we start with all the numbers from 0 to 1.
Yep.
And then at each step along the way, take the eraser. What we do at each step is we take the middle third out of each bit that we have left. So why don't you show what that might look like.
Maybe something like that.
Okay, so that's step 1, and now we take the middle third out of the bits we have left. And then we take the middle third out of the bits we have left. And maybe this is where our eraser will sort of reach its limit. Okay. Still have a little tiny bit there. And so we get a smaller and smaller amount each time.
Yep.
But what do you think happens here to what we have left after an infinite number of steps?
Well, eventually, I mean, you'll probably be left with just some points. Maybe like, if you include 0 and 1, they'll never get taken out.
Oh, okay, that's a good observation. Okay, good.
Maybe a point like 2/3, I think. I think it'll be on this bound here. That'll never get taken out.
2/3 will never be taken out. Okay, yeah, I'm not sure if you do take out the endpoints or not, but let's say you don't. That's a good point. 2/3 will just kind of live there and never be removed.
So if you take out an infinite number of intervals, you'll just be left with the points that are left behind by the intervals.
Okay, and do you think there are going to be a lot of those points left or a little?
Probably infinitely many.
Infinitely many, okay. So a lot. Another way to think about this, which is actually really neat, is to think about the numbers being written in base 3. And so when you take out the middle third, what you've taken out is all the numbers that start with 0.1 in base 3. So the numbers in base 3 can start 0.0, 0.1, or 0.2. The middle third always has a 0.1, so that's gone now.
Right.
And now each of these can start 0.00, 0.01, 0.02. And so you always take that out. Similarly here, you're going to be left with 0 and 2. And so what you end up being left with is all the numbers that are written in base 3 that only have 0s and 2s.
Yep.
So none of your numbers have 1 in them, have a 1 when you write them in base 3, which is pretty cool. But that actually shows, why does that show that there are an infinite number of numbers left?
Well, you know that it sort of relates to base 2, because you can just change all the 2's to 1's and you'll get all the base 2 decimals.
That's right. That's exactly right. If we just think of the 2's as being 1's instead, because we just some arbitrary symbol, we get all the decimals in binary. And so then we have an infinite number there. So that's cool. Now we're going to show 2 of the things I learned yesterday.